In this video, I'll demonstrate how to split the dataset into the training sample and another one for the holdout sample. So here first I have the sales territory case from the textbook, and in order to split this dataset randomly using SPSS, I'll have to copy the data first and then transfer that to SPSS. So here I'll have to type in the data, and then in the data view, I'll just paste the values that I copied. And then in variable view, I'll make edits to the names of the variables. So the first one is sales, second one is time in the company, the third one is the marketing potential, followed by advertising, then market share, and finally change in market share. So to split the data, just click data and then click select cases. Now click this part, random sample of cases, and then click this button. And then here you can identify the proportion of your observations that will be included in the training dataset, or you can specify an exact number. For this case, I have 25 observations and I want to include 15 in the training sample. So I'll specify 15 out of a total of 25. And then for the output, I'll just have to filter out and then press OK. And then now it will show you the filtered dataset. So here you have some observations that were randomly filtered out from the data, and these ones will be part of your holdout group. Now, in order to come up with the training database, just click data, select cases, and then click this one instead. So the if condition should be the last one, so the filter, and then here set that to 1. If it's equal to 1, it means that it should be part of the training dataset. So here for output, press copy and then name the dataset. So here I'll name this as training, and then I'll click OK, and then a new database will appear. So these are the numbers that are part of the training dataset, and these are the ones that were randomly selected, the 15 randomly selected observations from 25. Now to construct the other one, you just click data again, select cases, and then here if should be equal to 0. And then the output should be the holdout sample, and then pressing OK will show you the holdout sample. So these are the randomly selected observations that will be part of the holdout sample. So if you combine this with the training dataset, it should be equivalent, or it should be the same numbers with the original dataset. And now that you have these two datasets, you can try to validate the results of your analysis. So perform it first in the training dataset and then verify if you had equivalent or similar results with your holdout sample. Now, using the same dataset, I will now perform multiple linear regression. So to perform the test, click Analyze, go to Regression, and then click Linear. And then here you have to select the dependent and the independent variables. So for my dependent variable, it should be sales. And then for independent, I'll include all the 5 values of x. And then here for the model, I'll just choose enter first. And then later on, I will compare this to the results using stepwise, remove backward or forward. Now for us to validate the other assumptions, let's click some other buttons here. So for statistics, I will check covariance matrix. For me to check for collinearity, also collinearity diagnostics. Then to check for autocorrelation, I'll check Durbin-Watson, and then I'll click OK, continue. Now for plots, in order to verify the constant variance assumption, so I'll have to put z recid in y and z pred in x. And then I can also include the normal probability plot and all partial plots. And then press continue. And here are some other options, but I won't be adding anything else to this. And then now I'll just click OK and then wait for the results to appear. So SPSS shows me the following. So I have here in the first table the value for R square, the adjusted R square, the standard error, and the Durbin-Watson statistic. Now to test for the presence of autocorrelation, both positive and negative autocorrelation, we will compare this statistic to the lower and upper limits given in the textbook. So the critical values that we will compare this statistic to should be the two-tailed one, since we are trying to identify the existence of either positive or negative autocorrelation. So to identify the critical value, we need three values. We need the number of observations, which in this case is equal to 25, the number of independent variables, which is equal to 5, and the value of alpha over 2. If in this case, if we assume an alpha of 5%, then alpha over 2 will be 2.5%. And looking for that value in the table, we will get the interval 0.86 to 1.77. Now, the Durbin-Watson statistic is slightly lower than the upper limit, which means that it's inconclusive in testing the presence of positive autocorrelation. Now, to test for negative autocorrelation, we check 4 minus D instead. So that's 4 minus 1.762 or 2.238. And 2.238 is bigger than the upper limit of 1.77, which means that there is no negative autocorrelation in the residuals. And combining those two conclusions, since at least one of the two is inconclusive, our overall conclusion here is that it's inconclusive. We can't tell if there is positive or negative autocorrelation between the residuals. Now, looking at the next table, we have the ANOVA table. We have sum of squares regression and residual. We have the degrees of freedom, the MS values, the F-test statistic, and then the p-value. And we can see here that the p-value is very low, signifying that at least one of the independent variables is statistically significant. And looking at the exact values for the coefficients in the next table, we can identify which ones are significant. So first here are the unstandardized coefficients. We have the value for the y-intercept, which is negative 1113.788, and the respective slopes for the 5 independent variables. We have 3.612, 0.042, 0.128, and so on. Now, in order to test for the statistical significance of each coefficient, we need the standard error, and the ratio of the two gives us the test statistic. And once you have the test statistic, we can estimate the p-values as shown here in this column. And here we can see that some are significant at an alpha of 5% and some are significant at an alpha of 1%. Specifically, the y-intercept is significant at 5%, and the first 4 independent variables are significant at an alpha of 1%. The last one, however, is not significant at an alpha of 5%, which means that this independent variable of change in market share is not really statistically significant to the model. Now we can also see here some statistics in order to make conclusions about multicollinearity. So here are the values for VIF, and the values are relatively close to 1. They're not very high, which means that multicollinearity is not really an issue in this dataset. We can also verify that using the uh, correlation matrix in this table. So we can see that there are low correlation coefficients between the given independent variables, which is again similar to our conclusion earlier about VIFs. And here are some other tables. So here again, focusing on the coefficients table, we can see that this variable is not significant, and this is a possible variable that can be removed from the model so that we can improve our model. Now let's compare the results of multiple regression if we choose to remove this variable. So going back to the original dataset, I'll click Analyze, Regression, Linear, and now I will remove Change. So if I click OK, I'll see the results. And here you can see that certain values changed. The Durbin-Watson statistic is now lower, and the R-square is even lower, even the other values. If you compare that to the values that we got earlier, we can see that the values are slightly lower as compared to the values that we got earlier when we used all the 5. And again, that is normal because the variable that we removed is almost significant already at an alpha of 5%, which resulted to lower values for R square and adjusted R square. Now going back to the results of the new test, we can see that the overall model is still statistically significant with a very low p-value. And looking at the coefficients, we can see that all coefficients are now statistically significant. Multicollinearity is still not a problem. And then here, looking at the standardized coefficients, we can see that the biggest one is for marketing potential, signifying that marketing potential has the biggest influence in terms of the value of y as compared to the other values of x. Now let me test or let me use multiple regression again, and now I'll put change back, and now instead of using enter, I'll now use stepwise regression. So clicking OK will give me the following results. So now it shows you the steps involved in creating the model. So here we have statistics for the 4 different models. So stepwise regression came up with 4 different models. So you can see that for the last model, it has the highest value for R square, adjusted R square, and the lowest value for the standard error. We can also see here the statistical significance of all of those 4 models. And again, as you can see here, the F values were increasing from the first iteration to the last one, signifying a lower p-value, making thus the models statistically significant. And now here for the coefficients, as you can see here in the first iteration, there was only one independent variable. And then for the succeeding models, we kept on adding one more variable. So here in the last iteration, we can see that the model only has 4 significant variables, independent variables. So the change in market share was still not included here. And the values are all statistically significant as shown here by the p-value, and here the standardized coefficients are now showing different results. So marketing potential, this is similar to what we observed earlier. Marketing potential still has the highest value for the standard coefficients, signifying again that this has the biggest influence or biggest effect to the value of sales. Now here we can see a list of the excluded variables for each of the four models. So in the first model, there was only one independent variable. So here are the four independent variables that were not yet included. And from the first to the fourth one, we can see that it decreases because some of the variables here were being added to the model. And for the last one, there is only one variable that is excluded, and that's the fifth variable, because again the p-value is greater than 5%. So here are the correlation coefficients, so the pairwise correlation between all independent variables. And then we can also look at the charts. So as mentioned earlier, these are very important in making conclusions. We can see that the normal probability plot follows an almost straight line, so the normality assumption is satisfied. Thus, the residual plot shows us a relatively horizontal scatter plot of residuals, indicating that there is homoscedasticity or constant variance. And if you look at the partial scatter plots, we can see that uh, they all seem to follow linear relationships, which uh, uh, justify the use of a multiple linear regression model. So similar to our conclusion earlier, it seems to be better to construct a model with just four independent variables using stepwise regression. Now finally, I'll show you the effect of an, an error in removing or adding independent variables. We noticed earlier that among the five independent variables, marketing potential had the highest standardized coefficient. So let me now try to remove this, and let's try to observe what will happen to the results. So first, we can see that this one uses stepwise regression. We can see that the adjusted R squared, the last one, the last iteration, is relatively low. It's only 0.652. Here, the Durbin-Watson statistic is also low. In terms of the significance of all the models, we can see that actually got lower for the last one, but overall the model is still significant, signifying that at least one independent variable is statistically significant. Now looking at each coefficient for all the three models, we can see that the last model has just three independent, statistically significant independent variables. We have time, advertising, and market share. And then here we can see the excluded variables. So for the last one, change is not included. So again, we can see here the effect of removing a statistically significant independent variable to the statistics. For this case, again, it clearly reduced the values for R square, adjusted R square. It also provided a low value for the f-test statistic and a slightly lower p-value, and it also showed us new values for the slopes, and new p-values because we have an entirely different model. Finally, I'll use the same process, so regression, but now instead of using stepwise, I'll use enter. So I'll use all the four, excluding market potential, and then let's try to see the results. So here again, we can see that the adjusted R square is only 0.688 compared to our first one, which included all models, which gave a higher adjusted R square of 0.893. So the Durbin-Watson statistic is now 1.257. So again, this says that the test for autocorrelation is inconclusive. Now the overall model is still significant, and looking at the coefficients, we can see that uh, now all the four independent variables became significant, which is very different from our results earlier. Remember, in most of our iterations earlier, the change was always consistently excluded, but now because we removed a statistically significant independent variable, what happened was that the independent variable change suddenly became significant to the model. So we know that this is not really a statistically significant uh, independent variable when we compare all the models that we have created so far. And again, this is a problem when we accidentally remove variables that are actually statistically significant. So again, be careful in performing multiple regression. So you, as much as possible, try to perform different iterations for you to see the best models that can try to predict the value of y, and at the same time best explain the relationship between the dependent and independent variables.